Does anybody want to guess what the term linearization means? What about a line?
Making a curve into a straight line.
Yeah, it's actually pretty much exactly right. We're going to take a curve and we're going to make it into a straight line. Now, how can we take a curve and make it into a straight line? Why?
Take the derivative until you get down to just like.
What did you say?
Change the axes.
What do you mean by that?
Like the independent axis, put like, if it's y equals x squared, you can put x squared on the x-axis.
Oh,
That's basic.
no.
Is that some...
No. What? We could do that. Okay, what do you mean by that?
Like make it really small, little box.
Yeah, zoom in, right? So if you take a curve and you zoom in on it, if you zoom in enough, it's going to look like a line, right? Some curves you don't have to zoom in very far, particularly, well, especially when we're looking at certain regions on a curve. You don't have to zoom in very far and it'll look like a line. Some curves you have to zoom in a lot to make it look like a line. And I want to look at an example today that's in the book of one of those, that you have to zoom in a lot before it looks like a line. It's something that we want to do or understand how to do, because if we can make a curve look like a line is a lot easier to work with than a curve. So if we want to approximate values on a curve, we can use a line to do that. So this idea of linearization is we're going to use a line to approximate a value on a curve. And we'll look at some examples here that are pretty, they're pretty straightforward examples. And they're pretty, I think they're good, they display linearization really well. I didn't say that very well. Sorry. They're pretty practical, or at least they can be. So anyway, the idea here is we're going to zoom in on a line enough that it looks, or zoom in on a curve enough that it looks like a line. And basically what we're going to do is we're going to approximate a curve with a line. So this is a formula that we're going to use. What do you think L stands for? Yeah, the linearization. So the linearization of a function is equal to the function at some point plus the derivative of the function at that point times the difference between the x value and that point. And let me just draw a picture of what's going on here. So let's say we have a function that's a curve, and we want to approximate this function in some region. Now, one thing we need to understand is if I want to know what the value of this function is at some point, let's say I want to know what the value of the function is right here at maybe, let's say this is 2 on the x-axis, so maybe at like 2.1 something. Rather than plugging 2.1 into some big complicated function, I might be able to use a line to approximate it close to 2. I wouldn't want to use a point out here at like 6 to approximate the value of the function at 2.1. Why not? Why would I want to use a point here at 2 rather than a point at 6 to approximate the value of the function at that point? That's closer, right? That's an easy question, I think. So what we're going to do is we're going to use the idea of the tangent line. And let me draw a tangent line here for you. We're going to draw a tangent line at 2. And if you notice, the value of the function at 2 is very close to the value of the line at 2. In fact, because of the width of the lines and the curve, they still overlap here. So at values close to 2, this tangent line here is going to have values really close to the function. So within a small region, that line and that curve are going to be essentially the same thing. Does that make sense? Now we are going to have some error. We'll talk a little bit tomorrow about how we calculate the error. Basically, to actually calculate the error, we figure out what the value is on the line, figure out what the value is on the function, and we subtract it. But we can make a reasonable guess at the value of the function and have an idea of what the error is going to be without actually having to figure out the value of the function. And that is a practical thing too when we're talking about models in the real world. If we're going to model something, we want to know how far off we might be. So where does this come from? Let's talk about this real quick. Instead of a 2 here, let's put an A. And let me just get rid of this point here. I don't need that anymore. So what's going on in this equation? What's that?
You plug A into f of x.
Okay, so we're plugging A into f of x, and what we get then is the point here at A comma f of A, right? Okay, so where does this equation come from then? What is that? Let me say this. The L here, the linearization, is just the equation of this line. So this is like y equals something when we're talking about the equation of this line. So if I change this to y equals, well, it's close to mx plus b, but we have that f of a there. The f of a is the value of y at the point, right? So the value of y at the point we might call y1 here. This is the value of, a is the value of x at that point, so that might be x1. So this would be f prime of x1 times x minus x1. Does that look familiar? It's really close to something. What does the derivative tell us about a line? It tells us the slope. So if I replace that with m, it's getting really close to what? The point slope formula. So this is really just the equation of the tangent line. So it's some big fancy formula, but it's the equation of the tangent line. So what the linearization formula says is close to a point, close to the tangent point, or the point of tangency, the function and the line are pretty close to the same thing.